So we are looking at how to route traffic across autonomous systems while taking into account the policies that different autonomous systems want to impose. So the protocol that handles this is the BGP protocol. BGP exchanges many types of messages. We won't cover these different types of messages, but whatever messages are needed to enable routing across ASs, these messages are exchanged using TCP protocol. And this BGP operates as an application layer process listening on port 179. Within BGP, the same protocol is used, but there are two types of sessions. One session is called the EGP session, which facilitates inter-AS communications. Basically, this session is run over routers that are in different autonomous systems, and these routers are often directly connected with each other. iBGP sessions facilitate communication across routers within the same autonomous system. In this particular case, these routers need not be directly connected. The main role of iBGP is that whatever routes you have learned via eBGP, you will install those routes at all the routers within the AS. Confusing? This figure should help. So I have represented the ISPs by the clouds and organizations by these ellipses. Suppose this organization was something like IIT Bombay, it will have many routers within this, and there will be one router that is connected to the router of the ISP from which it is buying service. Often the organizations don't have to implement BGP, it is the headache of the ISP that is providing service. So how are things done within the organization? So we have many routers, and these routers may be serving different subnets within the organization. If you want to send packets to other subnets, these routers figure out based on OSPF or RIP. But if you have traffic that is outside your organization, all these routers are configured with a default route which specifies that they have to send this particular traffic to here, which then dumps the traffic into the ISP that is serving the organization. So this autonomous system that is representing this organization is often called a stub autonomous system. From now on, let's focus on how ISPs figure out routing information. These ISPs themselves will have many routers as represented here, and some of these routers will be serving other organizations. Let me represent an organization by the network portion, that is by the IP prefix. So this ISP will be serving many organizations, so it will have a set of such IP prefixes. Let me call this customer IP prefixes. This ISP as an autonomous system is going to implement an interior gateway protocol, that is intra-domain routing based on RIP or OSPF. And as part of this protocol, each of the routers knows how to reach any of these IP prefixes. The question then is, how do they figure out how to reach IP prefixes that are being served by other ISPs like this ISP or this ISP? So for this, they make use of this special routers called the border gateway routers. So these are represented by the green squares. So each autonomous system will have a few of these border gateway routers that interact with other border gateway routers of other ISPs. Basically, they establish these eBGP sessions with them. So this router is talking with other border gateway routers over eBGP. Similarly, this router is talking with this router over eBGP, so on and so forth. Pay attention, this is the crux of inter-domain routing. To begin with, each ISP knows its customer IP prefixes. These border gateway routers, by participating in the interior gateway protocol, figure out what this set of customer IP prefixes are. Much like in distance vector, where a router, when it is connected to different networks, it is going to announce to others that it can reach these networks at a cost of 0 because it is directly connected to them. So this is what in distance vector a given router is advertising to others. Similar thing happens, these border gateway routers to begin with will advertise to these other border gateway routers that they can reach all these customer IP prefixes After one such exchange, this ISP will know about the customer IP prefixes of this, customer IP prefixes of this, customer IP prefixes of this, because this border gateway router would have talked with these two to figure out customer IP prefixes of these both, and this border gateway would have talked in with this and figured out the customer IP prefixes of this. So now, much like in distance vector, you have to make a decision on which path your traffic should take. Now let's look at this particular ISP. Actually, let me name these ISPs. Let me call this A, let me call this B, let me call this C, let me call this. Now this particular ISP would have heard about this ISP D in the next round via this border gateway router. Now you must be wondering, this border gateway router has heard about D. How does this border gateway router know about it? This happens via the iBGP sessions. I'll get to that shortly, but for now assume that once this border gateway router gets some IP prefix information from its neighbors, it will convey it to other border gateway routers within. So thereby B is going to tell A about D. Similarly, C will also tell A about D. Now A now has two paths to D. Now unlike distance vector, what is employed here is a path vector. I will get into the details later. I had mentioned this earlier also. What basically happens is A is now informed of the path through the autonomous system the packets will take to reach the IP prefix that has been advertised originally by D. So let me call this prefix P. Now A has a choice. It can either go like this or it can go like this. Now depending upon, let's say if C were its competitor, it might decide to take this particular path. So the routing algorithm that inter-domain routing employs is similar to the distance vector with certain modifications in that it employs path vector. But the fact that to begin with, you start out with customer IP prefix informations, then you keep exchanging this information, and then slowly over time, you figure out how to reach the IP prefix informations corresponding to all the networks in the internet, except there is a catch. So what is the catch? The catch is the following. This particular ISP B, for example, would have heard of IP prefixes from D, but it can choose not to export these IP prefixes to A. In other words, it will not advertise the IP prefixes that it has learned from D. This is because of certain policy decisions. Similarly, for a given IP prefix, when it has heard from multiple ISPs, it may decide to go via a certain ISP and not to the others, again based on policy decisions. We will cover more of this under exporting routes and importing routes and also under path vector routing shortly. One final point I need to make here is that in this process of running inter-domain routing, these border gateway routers gather certain IP prefix information. Now this IP prefix information, they need to pass it to other border gateway routers so that they can further propagate it. Not only that, they also need to pass it to the internal routers so that they know how to route traffic. For example, if you have a packet that is destined to some network that is being served by D, you should know that you have to send it like this. So that information has to be conveyed. This is handled via iBGP sessions. Each border gateway router basically is going to establish an iBGP session with each and every router within the particular ISP and convey this information. So that is how a router here, for example, knows how to reach other IP prefixes. So it knows how to reach IP prefixes within the ISP via the IGP. It will know how to reach IP prefixes outside the ISP via EGP. Both of these control the forwarding table. I will cover more of this shortly. A lot of detail, right? Let me summarize. Any autonomous system that wants to participate in inter-domain routing has these special routers called border gateway routers, which employ the eBGP protocol to exchange IP prefix information with each other. The underlying route determination, that is which next hop autonomous system to take, is based on the path vector routing algorithm. This is a variation of the distance vector where you specify the entire path information. Unlike in other routing algorithms that we have covered, in this specific case, an autonomous system need not export all the IP prefixes it has learned. Depending on whose traffic it wants to serve, it often exports only a subset of these IP prefixes. We will cover more of this under exporting routes in an upcoming video. Again, unlike before, when there are multiple routes to a given destination where the choice of the route was based on optimality, here the choice is based on policy. We will again cover more of this under importing rules. Whatever information you have gathered as part of eBGP, what IP prefixes you can reach and via which autonomous system, this information is injected within an autonomous system via the iBGP sessions. So all these border gateway routers form a mesh of iBGP sessions with all the routers within autonomous system. As a consequence of all this, a forwarding table at a router is dictated both by the interior gateway protocol like RIP or OSPF as well as the exterior gateway protocol like the BGP. Now that we have understood the framework, we will explore it in a little bit more detail in an upcoming video.